All right, in this chapter we introduce the idea of tracking energy. Remember, energy cannot be created or destroyed. It's just shuffled from one storage mechanism to another one. The two things we focused on was thermal energy and phase energy. Thermal energy, again, due to the motion of the particles, and phase energy is due to the attraction between particles. We talked about the fact that we have different intermolecular forces, like hydrogen bonding, dipole-dipole moments, and London dispersion forces. So the first question says, draw energy bar graphs to account for the energy storage and transfer in all sorts of changes. Make up a sample situation and sketch the bar graph. So we have worksheets 1 and 2. You could select one of those questions to look at. And I'm going to look at the question. We've got a pan of water. That's at 25 degrees Celsius, and it's heated to boiling. So my system is going to be the pan of water. My thermal energy, it's starting at room temperature, 25 degrees Celsius. It's going to be heated to boiling, so I'm going to say it's going to end at a hot temperature. It's water, so initially it's going to start with 2 bars of energy, and it's heated to boiling, so it hasn't yet changed phase, so it's going to remain at 2 bars. So the energy is increasing, so it must have come into the system. Again, review worksheets 1 and 2, and then we took that energy bar quiz as to check your understanding. Then we talked a little bit more about molecular theory, that all matter is composed of tiny particles in random motion. And then we talked about whether the arrangement of particles is orderly, less orderly, or no order at all. So when energy is transferred to a sample of matter, either the particles speed up, the temperature increases, or they get pulled apart, but not both at the same time. So it says label which phases are present in each portion of the curve. Well, here it tells us that this is the melting point. So we can divide this up. And we're going to label this A, B, C, and D. So in A, we've got solid only. In B, we have solid here, and then it's going to liquid. In part C, we're just going to have liquid. And in part D, we're going to have liquid turning to gas. Label the sections in which thermal energy is changing and which ones where phase energy is changing. Well, we have a change in temperature here. So that's going to be thermal energy, ETH. Here we've got a change of phase, so that's going to be EPH. In this part here, we have a change in temperature, ETH. And here we have a change in phase, so that's going to be EPH. Energy calculations. So before you do any of the math, it's always important that you sketch a time temperature curve so you can focus on the changes. It says on the graph below, sketch the curve that describes the following. So we've got a final state. So I've got my graphs drawn in now. So it says on the graph left, we're going to do the situation, initial state and final state. So initially it's starting at -10, and it's water. So it's going to, the final state, it's going to be liquid water at 0 degrees Celsius. So the first thing it's going to do is it's going to need to get up to the melting point, which is 0 degrees Celsius. The final state is 150 grams, so 100% of it is melting. and it ends up as liquid water at 0 degrees Celsius. So that's what the time temperature graph is going to look like for number 4. For number 5, it says on the graph on the right, so that's the curve that describes the following. We've got 200 grams of liquid water at 40 degrees Celsius. So I'm going to start this at 40. And the final state is half of the water has boiled away at 100 degrees Celsius. So it's going to increase in temperature till it hits 100 degrees Celsius. And then half of it is going to boil away. So the rest of this portion of the graph is not going to be used, and we're only going to allow half of it to boil away. So when the temperature of a solid, liquid, or gas is changing, the energy transferred by heating is going to be involved. Let's go on to the next calculation question. Calculate the amount of energy required to bring about the change in number 4. So in number 4, remember our graph looked like this. We had -10. It increased in temperature until 0 degrees Celsius, and then it melted. And our amount of ice was 150 grams of ice. So we've already got our heating curve done. We're going to need 2 different calculations. So for the first calculation, I've got a temperature change. So for 1, it's going to be Q equals mc delta T. We're solving for Q, so Q is my unknown. Whoop. My mass is 150 grams, and my delta T is, we're going from -10 degrees to 0, which means that I'm going to have a 10-degree change in temperature. So now I'm going to substitute my numbers in. Now I have to look up the specific heat of water. I can find the specific heat of water on question number 3, or worksheet 3, which is the one we did here. So when I look at worksheet 3, I see that the heat capacity of solid water is 2.1 joules per gram per degree Celsius is the C of ice. So I'm going to need that number. Substitute that into my formula, 2.1 joules per gram per degree Celsius, times my delta T, which was 10 degrees Celsius. So Q will equal Q will equal 3,150 joules. I'm going to need how many significant figures? I've got 2 significant figures in my mass, so I'm going to say that I'm going to need 2 significant figures in my question. So that's going to be 3,200 joules. Calculate that's for the first part of this graph. The second calculation I'm going to need to do is for this section of the graph here. We've got a phase change going on, so the formula I'm going to need is Q equals M H, and it's melting, so I'm going to need the heat of fusion. I look on worksheet 3 and I see that the heat of fusion for water is equal to 334 joules per gram. So I am solving for Q. My mass is the same, as it says all my ice is melting, so 150 grams. And my HF is 334 joules per gram. So I'm going to just substitute the numbers in. And when I put that in my calculator, I get significant figure-wise, again, I'm going to need 2 for this. So Q would equal now the last step is to add these 2 together. So for the calculation for number 5, you're going to need 2 different calculations. So calculation number 1, the answer you should get is 5,000 or 50,000. And then you're going to do the next part of the calculation. And remember, the change in number 5, you only have half the water boiled away. So the change in number 2, you're going to be using half the mass. So when you use half the mass, you're going to end up with a total of joules. You add these 2 numbers together, and the total amount of energy will be equal to okay. Be sure that you've shown the work for all these for this question. If you need to use a separate sheet of paper, feel free to do that because there's not a lot of room.